In this video, we are going to discuss singular points, including isolated singular points. This is our overview slide, which we'll spend less than 5 minutes on before we go over each topic in more detail and with more examples. To start, we'll define what a singular point is. So a point z0 is called a singular point of a function f if f fails to be analytic at z0. But it is analytic at some point in every neighborhood of z0. In the main part of our video, we'll take a closer look at what this means to be analytic at some point in every neighborhood of z0. Our next definition is a singular point z0 is said to be isolated if, in addition to being a singular point, there is a deleted neighborhood where the modulus of z minus z0 is less than epsilon and greater than 0, of z0 throughout which f is analytic. And again, we'll take a closer look at this definition in the main part of our video. We do have an example here that we will cover in more detail, but let's go over it just really briefly to identify the three isolated singular points of the function z cubed plus 1 divided by z cubed times z squared plus 1. To look for singular points, we need to look for points where this function fails to be analytic, and in particular, we're going to look to see where we have division by 0. The first thing we do is factor this out completely, so our z cubed times z squared plus 1 is equal to z cubed times z minus I, z plus I. So we can see that the denominator has potential, or is equal to 0, when z is equal to 0, z equals I, and z equals negative I. So these are our three singular points, 0, I, and negative I. To show that these 3 points are isolated, we need to find a neighborhood. And the neighborhood consists of the point z, where the distance between z and z0 are less than epsilon. In other words, we're within some radius. We're in the interior of a circle of epsilon radius, and it's centered around z0. But we also have that z is not equal to z0. So we've punctured the disk. We've taken out our offending singular point. And what we want is, in this deleted neighborhood, we want to be f to be analytic. So in this case, I have 3 singular points, I, 0, and negative I. So if I want to find a neighborhood around I, this singular point, that is totally analytic, well, first it's a punctured or a deleted neighborhood, so we take out our I. So this is just punctured out. So think of this neighborhood without this point I. Maybe I'll dot it in red to say it's not really there. We've deleted this point I from our neighborhood. And now we want to make a neighborhood where everything's analytic. So we can make our neighborhood as long as we want, as long as we don't run into this point 0, our closest other singular point. So in this case, since I and 0 are 1 unit away, I just took epsilon sub I equal to 1/2. So this is my deleted neighborhood where I'm totally analytic, and that is how we will show that z equals I is an isolated point. Similarly, we can take epsilon, a neighborhood of radius 1/2 around 0 and a radius of 1/2 around negative I, and show that they are also isolated. We have 2 other facts. The first one is if a function is analytic everywhere inside a simple closed contour C except for a finite, and this is important, a finite number of singular points, z1, z2 up to zn, those points must all be isolated, and deleted neighborhoods about them can be made small enough to lie entirely inside C. And to see this, we would consider one of the points z sub k. And it's sort of like this example here. We have a finite number of isolated points. We have exactly 3. And we considered this point here, I. The radius of the needed deleted neighborhood can be any positive number that is smaller than the distance to the other singular points. So again, we took the radius equal to 1/2 because it's smaller than the distance from I to any of the other singular points. And in this case here, we also have a closed contour. So if we want to keep our neighborhood in the closed contour, the other thing we need to do is take our radius smaller than the distance from z sub k to the closest point on the closed contour. Finally, our last point is sometimes it is convenient to consider the point at infinity as an isolated singular point, and this will become more useful later on in other chapters. Okay, so that's it for our overview. Let's go back and take another look at singular points. We will start with the definition of a singular point. A point z0 is called a singular point of a function f if f fails to be analytic at z0, but is analytic at some point in every neighborhood of z0. It's fairly straightforward to understand what it means that f fails to be analytic at z0. Let's take a closer look at what it means that it's analytic at some point in every neighborhood of z0. I will start by drawing a small neighborhood around z0. That's the interior of a circle with z0 at the center. And what this definition says, well, first, f fails to be analytic at z0, but it will be analytic at some point in every neighborhood of z0. So in this neighborhood here, this neighborhood bounded by the z circle, there's some other point. Let's just say it's this point here that is analytic. And the idea is we can get a neighborhood infinitely small, and I can't draw infinitely small, so I'm just going to draw a smaller circle, this green circle. So we're looking inside the disk. And now if we look here, there's going to be at least one point that's analytic. Let's just say it's this point here. So the function f may go crazy at z0. So all over the place near z0, the function may fail to be analytic, but there's going to be at least one point, no matter how small the neighborhood you make it. So there's going to be some other point to z0 that is analytic. No matter how closely you look at z0, you will be able to find another point that is analytic. We will start with the example of identifying three singular points of the function f of z is equal to z cubed plus 1 divided by z cubed times z squared plus 1. To find where this function fails to be analytic, I'm going to look at where we have division by 0, and I'm going to start by looking at the denominator and going ahead and factoring my z squared plus 1. So what I get is z cubed times z squared plus 1 is equal to z cubed times z minus I, z plus I. So the denominator is equal to 0, or can at z equals 0, z equals I, and z equals minus I. So these are my three singular points. A singular point now is said to be isolated, an isolated singular point, if in addition to being a singular point, there is a deleted neighborhood where z minus z naught is less than epsilon, and now instead of greater than or equal to 0, we have strictly, this modulus of z minus z naught is strictly greater than 0. That gives you the deleted neighborhood of z naught throughout which f is analytic. So let's look at this definition. Let's start by looking at this idea of a deleted neighborhood. Here I have my point z naught, and here I have my neighborhood. So again, it's a disk, the interior of the circle with radius epsilon. And again, the distance, it's all the points z, where the distance between z and z naught is less than epsilon. So what you get is this interior of a circle. But now you also have the deleted neighborhood. The distance between z and z naught has to be greater than 0. So what that means is from this disk, we're going to remove this point z naught. It's sometimes called a punctured disk. We just take that one point out. That's the idea of the deleted neighborhood. So we know z naught fails to be analytic. Now we're going to look at the rest of the disk without looking at z naught. So what happens there? In this case, it's isolated if there's a deleted neighborhood of z throughout which f is analytic. So if we just remove this one point, then everything is analytic in this neighborhood. In that sense, z naught is isolated because it's surrounded by analytic points, and it's the only singular point in the neighborhood. It has no company. In light of this new definition, isolated singular point, let's look at the previous example where we identified three singular points of z cubed plus 1 divided by z cubed times z squared plus 1, and we found the singular points to be 0, I, and negative I. I'm going to start then by graphing my singular points in the complex plane. Here I have 0, I have I, and I have negative I. I'm going to claim that all three of these points are isolated singular points, and to show this, I need to find a deleted neighborhood for each of these points. So I need a deleted neighborhood for I, a deleted neighborhood for 0, and a deleted neighborhood for negative I, such that the deleted neighborhood is analytic throughout. So let's look at I first. What I can do, and we're going to use this technique again at the last example, is I'm going to look at I, and I'm going to find the nearest other singular point, and that would be 0. The distance between I and 0 is 1 unit. So that means I can take any epsilon less than 1, and in this case, so I'm going to take epsilon of I is equal to 1/2. That's certainly less. And when I draw a disk around I, you can see it will not include any of the other singular points. It does not include 0. It doesn't include negative I. And since these are the only singular points, that means this disk here is analytic throughout once I take out the I. So in other words, this is my neighborhood, z minus I, so the modulus of z minus I, the distance between any point in this disk and I is going to be less than 1/2, so it's within the circle, but it'll be greater than 0. So in other words, the greater than 0 is what removes this I. So everything in this neighborhood is analytic, which makes I a singular point. And honestly, to show the neighborhood for around 0, I could take the same radius. So epsilon of 0 could also be 1/2. But, just to show this, I could have chosen epsilon of 0 to be 3/4 because that still will not hit any other singularities, or I could have chosen an even smaller one, this tiny one here. But you can see that here, let's just take epsilon 0 equals to 1/2. That will still avoid any other singularities. So I found a neighborhood where a deleted neighborhood of 0, where everything is analytic. Similarly for negative I, epsilon equals 1/2 will be sufficient to avoid any other singularities. So what I have shown is these 3 points are all isolated singular points. Our next example is to identify the isolated singular point of the principal. This is not just log z, but it's the capital L, the principal component, log z, which is equal to natural log of r plus I theta, where r is greater than 0, and theta is between negative pi and pi. And for log, we know 0 is a singular point. I'm also going to take a quick look at this r greater than 0 and theta between negative pi and pi. So our 0 is greater than 0, so it's, whatever. The radius goes out to infinity. Our theta, because this is the principal branch, our theta has to be between negative pi and pi. In other words, we have this branch cut at theta equals pi. So theta equals pi is off limits for this principal branch. And this branch cut is what makes this 0 not an isolated point, since every neighborhood around 0 contains a point on the negative real axis, which is the branch cut. In other words, if I try to draw a really small neighborhood around, and I'm going to do this in green, around 0, no matter how tiny I make this circle, I'm always going to include part of the branch cut. So 0 here has company. It has this entire axis, any point on this axis that is also like a singular point where f is not analytic. Our last example is to identify the singular points of 1 over sine pi over z. And also, in addition to identifying the singular points, we're going to determine if each of the singular points is isolated or not. To find the singularities, I'm going to look where we have division by 0. So first, looking at sine of pi over z, we have division by 0 when z equals 0. Then when I look at sine of pi over z, this denominator here, to look and see when it's equal to 0, well, sine is equal to 0 when we have an integer multiple of pi. So that means sine is going to be 0 when z is equal to 1 over n equals plus or minus 1, plus or minus 2, etc. And I just have that graphed over here. And I've written out then the singular points of 1 over sine of pi over z are z equals 0 and z equals 1 over n. So the next thing to determine is if these singular points are isolated or not. To do this, we need to look at neighborhoods around z equals 0 and also z equals 1 over n and see if we can find a neighborhood, a deleted neighborhood that is analytic throughout. When I was trying to determine if these singular points are isolated or not, it's a mistake to look at this graph here because this is about sine. It's not about our function 1 over sine of pi over z. So I made a little chart. Graphing it was going to be complicated. So I just made this chart of values of z, values of sine of pi over z, and then values of 1 over sine pi over z. And just a comment, I put this intermediate step because it helped me see what was going on. Starting at z equals 0, so here we immediately have something that's undefined, so our final function is going to be undefined. And this is what we had talked about, that z equals 0 is a singular point. Next, I looked at z equals 1/4. So sine of pi over 1/4, that's the same thing as sine of 4 pi, which is equal to 0. And this is also what we were talking about here. Z is equal to 1 over n. When n is equal to 4, this is exactly this case here. So we had identified this as a singularity as well. So that's good. Z equals 1/2. So when I have sine of pi over 1/2, that's the same thing as sine of 2 pi. Again, this is undefined. And this is exactly the case over here where z equals 1 over n when n is equal to 2. So that's good. We had identified this as a singularity. When I have z equals 3/4, then sine of pi over 3/4 is the same thing as sine of 4 pi over 3, which is equal to negative 8.66. So I can calculate my function 1 over sine of pi over z, and I get negative 1.154. And this is what we expect. We should not have expected a singularity because in this case, our z, is not 1 over an integer, it's an integer over an integer, right? It's not 1 over 4 or 1 over 3, it's 3/4. So that's good. Now we have z equals 1. So now we have sine of pi, which is equal to 0. And again, that follows our pattern. N is equal to 1, z is equal to 1 over n. So that was going to be a singularity. We were expecting a singularity. Z equals 2. We're going to have sine of pi over 2, which is equal to 1, which means our function here has a value of 1.154. So far, everything looks good. And I've denoted where our singularities are. They are at z equals 0. And then again, for z equals 1 over n. And in this case, I put n equals 2 and 4 and 1. So 1, 2, and 4. But you also know there's a singularity when n equals 3 and z equals 1/3, when n equals 5, z equals to 1/5. And one thing you will note about these singularities, as n gets larger, our z's get more and more compact. So what I mean by that is when we have our singularity at z equals 0. And now let's look at the singularity when n is equal to 1, z is equal to 1. So it's over here. That's where our singularity is, at z equals 1. When n is equal to 2, our singularity is at z equals 1/2. When n is equal to 3, our singularity will be at n equals 1/3, which is somewhere around here. When n is equal to 4, then our singularity is at 1/4. This is 2.5. When n is equal to 5, our singularity is at 1/5. When n is equal to 6, the idea is that these singularities start to come closer and closer together. The closer you get to 0, the closer the singularities are. So that's going to be an important point. I've moved my drawing here, and the point is all of the singularities are isolated except for z equals 0. Let's start with all the other singularities are isolated. So here at 0.5, we look at the next closest singular point, which is this one, which is 1/3, and we can definitely draw a radius as long as it's less than the distance between 1/2 and 1/3. We can isolate this singularity. If we looked at the singularity over here, this is the singularity at 1/4, 1/4. We could look at the distance between the singularity 1/4 and 1/5. As long as we draw a circle of radius that's smaller than the distance between those 2 points, we can create our neighborhood, our punctured disk, our deleted neighborhood, where everything's analytic. So we can do this for each point. All these other singularities of this nature, except at z equals 0, we look at the next singularity that's closest and then draw a radius that's smaller than the distance between the singularity we're considering and the next closest singularity. But this won't work for 0. So 0 is not isolated because every deleted neighborhood of z equals 0 contains other singular points. Remember, the singular points get really compact by the time you get to 0. So given an epsilon, there always exists some m greater than 1 over epsilon that will include a singularity. We are just about done with this video, but we have a couple of more points. The first point is if a function is analytic everywhere inside a simple closed contour except for finite, and this word finite is important, number of singular points, z1, z2 up to zn, those points must all be isolated, and deleted neighborhoods about them can be made small enough to lie entirely inside C. Let's take a look at this. Let's consider one of the points, z sub k. In this case, we're going to look at z1. So let me put this little red dot here. That's our point that we're going to say is isolated. The radius of the needed deleted neighborhood can be any positive number that is smaller than the distance to the other singular point. So in other words, z4 is the singular, if we have a finite number of singular points, 1, 2, 3, and 4. Z4 is the closest one, so this distance here, whatever this distance here is epsilon, as long as we choose a radius for our neighborhood to be smaller than epsilon, one other thing to consider, that was a really bad circle. The other thing to consider is if our curve, let's see, where is it set? And also smaller than the distance from zk to the closest point on C. In this case, the closest point on C is maybe this point. So this distance is smaller than the curve on C. So we could choose any epsilon less than, for our radius, less than the distance between z1 and z4. Then if the curve actually happens to be something like this, then instead of our radius being the distance between z1 and z4, we just choose the radius to be something less than the distance from z1 to the smallest point, the closest point on C, and then we get another neighborhood where we can say everything's analytic. So as long as we have a finite number of other singular points, we just choose the one that's closest, and then we compare the distance from our z sub k to the closest other singular point, and also the distance from z sub k to the curve. We choose whichever one's smallest, and then we choose a radius smaller than that number. This here is exactly the technique we did in our first example when we tried to determine, or when we showed that they were isolated. We had our 3 singular points, and then we looked at the distance between the singular points, and we just chose an epsilon smaller than the distance, and we said, okay, that's our neighborhood. Once we do the punctured disk where we take out our singularity, everything in the disk will be analytic. I also want to mention this only works when there's a finite number of singular points. And an example of this was our third example when we were looking at the singular points of 1 over sine pi over z. We said that we have a singularity at z equals 0. However, that point is not isolated, and that's because we have an infinite number of singular points. And so these singular points get infinitely close to 0. It doesn't stop, and then at one point we say, oh, this is the point that's closest to 0. There's an infinite number that converge on 0, and that's the reason why this z equals 0 is not isolated. And also that's why in this statement we need a finite number of singular points. And the last thing I want to say is sometimes it's convenient to consider a point at infinity as an isolated singular point. And to be specific, if there's a positive number r1 such that f is analytic for modulus of z is greater than r1 but less than infinity, and I'm just going to draw that. So z is analytic everywhere outside the circle of radius r1 all the way to infinity, then f is said to have an isolated singular point at infinity. And this becomes convenient later on for later results. To review what we have covered in this video, we talked about singular points, including isolated singular points. First, we defined what a singular point was, which is a point z0 is called a singular point of a function f if f fails to be analytic at z0 but is analytic at some point in every neighborhood of z0. And then a singular point z0 is said to be isolated if, in addition to being a singular point, there is a deleted neighborhood. Those are the points z whose distance from z0 is less than epsilon but greater than 0, throughout which f is analytic. And we had this example here where we have z cubed plus 1 divided by z cubed times z squared plus 1. We found the singular points by looking at where the denominator becomes 0, and that's at z equals 0, z equals I, and z equals negative I. And then we determined that the 3 points are all isolated. And for example, just looking at z equals I, to find a deleted neighborhood, we just looked at the next closest singular point, which was 0. Their distance is 1. So as long as we take an epsilon less than 1, we'll have a neighborhood around I where f is analytic. And therefore, since we could find that neighborhood, we say that I is an isolated singular point. It has no company around it that's also singular. It's isolated. Similarly, we can show that z equals 0 and z equal I are also isolated. We had 2 more points. If a function is analytic everywhere inside a simple closed contour C except for a finite, and that was important, finite number of singular points z1, z2 up to zn, those points must all be isolated, and a deleted neighborhood about them can be made small enough to lie entirely inside C. And the explanation to see this is very similar to what we did here, and that the radius needed for the deleted neighborhood can be any positive number that is smaller than the distance to the other singular points, and is also smaller than the distance from zk to the closest point on C. Our last note is that sometimes it is convenient to consider the point at infinity as an isolated singular point, and that comes in more useful in later chapters of this book. So that's it for this video. Thank you for watching.